Hello, this is Jeffrey Fox again from the I-590 Data Science class discussing open source software and projects. Here we get into some aspects of the big data applications that we've already sort of developed the basic classification for. And the first few slides just give some other places where we have sources of use cases. Remember, we went in most detail through the NIST survey. Here we have a survey from a group of 6 well-known authors in high-performance distributed computing. And they have looked at 6 applications listed here: biology, climate, astronomy, oceanography, and fusion. Important large-scale simulations, and they've divided the problems up according to these characteristics here: execution, architecture, how the communication mechanism, the coordination mechanism, and the overall environment. And if you look at characteristics, you will see that there's important use of data flow, which is roughly the same in our context as workflow, which is needed to link different jobs together. Communication, we have streams, pub/sub, writing to files, sending messages, and that's again points out how different programs do different things, sometimes because it's needed by the program, and sometimes because that's just what the people who developed it did. So these are all large-scale applications running on typically multiple supercomputers in a distributed fashion. Here we have, go back to the NIST survey, the security and privacy group had 10 different use cases which were not done in the same fashion as the 51 use cases: consumer digital media, Nielsen home scan. These are obviously commodity applications which have some privacy issue, data analytics from the web. Of course, health is full of important security issues. Here we have 3 separate health areas. Cybersecurity is obviously very important area with all sorts of news items from time to time about actions in that area. The aviation industry is very sensitive to security because the consequences of a break-in or something like that are so severe due to the obviously serious problems if an aircraft gets compromised while flying. The unmanned sensor data is growing in importance as we have more and more unmanned vehicles flying with greater and greater capabilities. And then in education, we have a lot of important work to be done understanding performance data, but that work has to respect the privacy. Here we have the report from the National Research Council, massive data analysis. This comes from a part of the report aimed at statistics. And so these are all statistics related areas. And we have basic statistics. That's illustrated with what I call MR stat in my classification, MapReduce statistics, adding over, overall standard deviations, averages, correlations, things like that. Then they notice the importance of the order n squared problem, which they term the generalized n-body problem. When you have lots of points in a problem, whether those points be particles, people, websites, they're all linked in some fashion, which corresponds to the so-called force between the particles in the particle case. And you can actually think of these as actually forces between the entities when the entities are not particles. And a particularly important problem is when all particles are connected to each other. That's the n-body problem. And in big data, there are lots of cases where all data points are linked to all other data points. We've been pointed out the importance of graphs, and there are many sophisticated graph algorithms which need to be implemented properly. This is where software like Giraffe and Praeger comes in, also Pegasus. Linear algebra is absolutely critical in almost everything, and a lot of machine learning algorithms have linear algebra at their core. Then we have the so-called things coming from the optimization field, where you have approaches like linear programming, which are well known to be not so easy to parallelize, and those deserve some study. They typically are not always huge problems, so you can actually get away with it. There's here what they call integration, is what I call global machine learning with algorithms like latent Dirichlet allocation. And then the final thing, which I didn't really properly study in my analysis, are alignment problems. And these are comparison problems, which are a little like web search, where you take BLAST, you take one sequence and you try to compare it with all other sequences using the overlap between sequences calculated, in this case, by the BLAST program. That's very similar structure to search problems, and that's actually, or even recommender problems, where you're trying to find items that are near each other. That's actually what you're typically doing with BLAST. And that's why MapReduce is suitable for this problem, because it's the same overall architecture as search. Now let's just have, in this section, we're starting a set of subsections which go into details in some areas of the application structure. The first one we're going to look at is classical databases, which are part of the search query index category. So obviously this has been studied for a long time, and actually it's not an area I'm a great expert at. We have tables, which are so-called schema on write, namely when you write the data, you actually fix the schema. And then you have highly optimized queries, which have been investigated in great detail for a long time and highly optimized in the SQL language. Obviously, one example here is OLTP, online transaction processing, and their traditional databases are highly optimized, because these are areas where there's actually not a huge amount of computing, because the amount of work done when you, I don't know, update your bank account is not huge, but reliability and robustness is extremely important. And also, when you go to your ATM, you want your account to be found very quickly. So you need very good indices and quick response to the typical queries. And as I mentioned, fault tolerance is absolutely essential. And although you can scale this to pretty large systems, these robustness constraints lead to difficulties with parallelism. And the data here is large, but possibly not super large. And here you have, here I pointed out 100 million people at 10 megabytes of data is a petabyte, which is not, I mean, given you have 100 million people, that's not an enormous amount of data. When you start looking genomics per person, then you get to much larger data sets. This picture here shows the classic table structure studied in databases. Of course, if you look at the past few years, there's been a great debate between the database community and the cloud community about traditional approaches to databases, or the MapReduce approach, which often uses NoSQL like HBase for storage. And it's, in some sense, I think this argument is now sort of over. Both sides are right. Traditional databases are wonderful, and Hadoop and NoSQL are wonderful. They have different optimizations. And you can say you can actually view MapReduce as exposing parallelism, which is possible in databases, but maybe typically not been an emphasis in commercial products like that, those from Oracle, because the fault tolerance issues were more important than the parallelism issues. So Hive plus Hadoop can be viewed as one way of getting a traditional database, but with different optimizations which allow you to scale to much larger um, systems. Now, another facet of this is relational databases were not built to do clustering or recommender systems. And so in one way that there is a difference between MapReduce or iterative MapReduce and databases is you're just solving a different problem. In one, you're updating bank accounts, and the other, you're running clustering. And there are various numbers out about the cost impact of these different optimizations. So if you look at the price of a database per year, it's meant to be for a terabyte of data about $1,000 or so for a Hadoop cluster, but 5 or even more, 5 to 50 times more than that for commercial relational databases. Relational databases, as they don't scale so well in distributed memory parallelism, often need larger, more expensive servers, whereas Hadoop scales on commodity, cheap systems. If you work in this area, you'll find terms like extract, transform, load, and data warehouse as important aspects of how one deals with the enterprise data with these technologies. And ODS, operational data store, is another useful term that one will come across. So here we have some comparison from Cloudera. I give you the link here at the bottom here. Here you have schema on write. That says you have a fixed schema. You have to write with that schema. And here you have schema on read, which means that you can effectively define the schema for the data you're reading from a less structured storage mechanism. So you have the static schema. The data here is native, more dynamic schemas with dynamic parsing, and you query in native format. And obviously here you query in the classic relational database format, and you have a rather structured fashion for adding new attributes with new columns. And you can hear in the cloud approach, you can do everything dynamically. And as I said here, this is good for known unknowns. Namely, we know exactly what you want for a bank account. Here, when we're looking at social media or something, it's good for unknown unknowns. We don't know what we're doing, so we need a less structured specification. Here we have the problems in the relational database approach, which is the fact that the volume and the velocity and the variety of the data leads to problems, and which is basically all comes down to performance. Or what's sort of related is cost, because you only have a certain amount of money, so you will, if you can only buy a system of a certain performance. And here is just a typical process. Again, this comes from the Cloudera presentation, where we have enterprise application, online data processing. We do our ETL, and then we go to the data warehouse, which is then queried to get results. And so here's from another talk from Berkeley, data science class, about ETL, giving the data warehouse, which then can be looked at in different fashions, analytics with MapReduce, or maybe with classic relational databases. So here we see this taking a relational database and then transforming it, and then doing significant Hadoop type queries. And you can actually feed that data, ignore the warehouse, which is, if you like, the classic approach, and then store things, then use the pure cloud approach. So if you look at a standard talk from a big company, they will do everything. Here's the IBM Big Data Platform. It has Hadoop, it has streams, it has warehouses, and it has semantic type technologies. And it has visualization, it has acceleration, it manages everything, and puts in lots of different applications. And there's predictive analytics and content analytics. These are all the data analytics structure which we have. So this it's very difficult to deduce anything from here, and whether it works very well, who knows. Given it's IBM, it probably works excellently because they put a lot of effort into commercially relevant systems. Here is the same approach from Oracle. I'm going to talk by Oracle. And again, you basically see everything: big data, unstructured data, metadata, analytics, reference data, master data, transaction data. And these things here are shown again in here. And then they have all these different functions around here. And you can, of course, do everything. And again, it will probably cost more than some other possible solutions. So now we go on to NoSQL. That will be in the next lesson.